All right. Welcome, everybody. We'll get started here in a minute. So good morning, good afternoon, good evening, wherever you are, and happy Earth Day. If you could go in the chat and just tell me where you're tuning in from for this community conversation. And hi, Danya. What a pleasant surprise. Yes, Danya is in Tennessee. Let's see how many countries we get. Oh, Carl Storms. Jacob, of course, from Boston. David Koch from Philadelphia. Anwar from Paris.
Nice.
Harsh from India. Thomas. Joseph, well, they're starting to roll fast from Novi. Know that well. Matt from Los Angeles. We got, yes, Saul from New Zealand originally, but now in Boston. Frankfurt, Germany. Yes, it is a global affair today, this morning, this afternoon, whatever it is. So we'll give a couple more minutes here as people join in. If you just joined late, shout out where you're at in the chat. Well, I think we'll start now. Everybody stop chatting out where they're at. So welcome everybody. Let's kick it off. Welcome to the new community conversations hosted by the Autodesk community. Our community conversations are the new live virtual events designed to allow you to gain expertise, connect with leaders, and grow your community network. My name is Sean Hurley, and I'll be your community host. We're joined by the talented Jacob Small and Sol Amour. Today, we will be discussing all things Dynamo geometry, model types. So let me introduce myself. I'm Sean Hurley, Autodesk Community Engagement Manager. Been at Autodesk many years, also the blogger behind Between the Lines. And joining me.
I'm Jacob Small. I'm off camera. Let me fix that. I am a designated support specialist out of Autodesk Boston office and Dynamo Form Junkie. I've been with Autodesk for 3.5 years now, helping some of our larger customers with enterprise business agreements ensure that they're adopting our software successfully overall.
Cool. And hello, everyone. My name is Sol. I am the Dynamo product manager. So it's my remit to guide the evolution of the software as we move forward into the future. So making Dynamo all that it possibly could be. I describe myself as a curious human being, also based here in Boston, Massachusetts, but originally from New Zealand. If you can't tell by the accent, I've been at Autodesk now for about 2.5 years. Ex-industry as well, so architect by background.
Excellent. Thank you, gentlemen. So we do have some rules. Everyone's line's been muted to reduce the background noise. And we would invite you to share your video camera just to kind of give us a sense of community and this time we can't be together physically. This is a conversation, so use the Zoom, raise your hand to ask a question and in the chat. And the event is being recorded. So for those that weren't able to participate, and they could yell out where they're from too in their room. It'd be a little weird, but it'd be fun. But anyway, you'll be emailed that link for the recording after this session. Lawyers require us to mention that if we give any forward-looking statements that you understand that your purchases are based on what we have in the products now. That's just a legal requirement, so that don't base any of your purchases on anything that we say might happen in the future or we're looking into. Community conversations are a relaunch of our previously hosted customer success meetups, where we aim to provide opportunities for engineers, designers, artists, and makers to meet in a safe live virtual setting to share expertise, get to know leaders in their field, and grow the community network. This is about you and part of the community. And in the future, we'll have opportunities for you to present your expertise. In this space, we'll be bringing you expert speakers that that could be Autodesk employees, customers, partners, and students to gather around knowledge sharing where questions and discussions will be sparked. And we hope we forge new connections amongst the community. The sessions are always supported by the Autodesk community managers to help guide the conversations, feed important insights back from the community to Autodesk, and support participants in getting connected and the expertise you need, excuse me. So with that, I will hand it off to Jacob and Saul.
Awesome. Well, welcome everybody. Glad you could join us today. This is a continuation of the Dynamo Office Hours series that we started last year. So you'll notice that this is session number 8. And if you joined us last week, we discussed Dynamo Geometry abstract types. So today we start looking at model or physical types. So things that you could touch in the real world if you could touch a computer. Next group, please. All right, so today our agenda is as follows. We're going to do about a 15-minute presentation when we dive through a series of slides based around this model of physical geometry inside of Dynamo. We're going to give a little live demonstration, so cue the danger music on that one. We had some mild technical difficulties earlier on, so we'll see how that goes. But we do have a GIF in the slide deck that'll show you the intention of what we're going to live demonstrate today, and we can talk through that graph. And then also we have a little bit of a Q&A session at the end as well. So please do ask all the questions you want specifically about what we talk about today, but also any generic Dynamo questions as well, any burning itches you need to scratch. So today we're going to talk about sort of the data type hierarchy. So last week we talked about the abstract types. So this is things like vectors, bounding box, and topology, and all of the interesting sort of interactions that they had. This week or today, we're going to talk about sort of geometry types, or otherwise known as model types. So if you hear the word geometry or model or physical in this case, we're basically interchanging all of those words. These model elements are things that you would be able to sort of touch or interact with within a piece of software, whereas the abstract typologies are sort of more mathematical based and ethereal in nature. So today we're going to cover points, curves, surfaces, solids, and meshes. So the first thing that we're going to cover today is points. These are going to be bound by XYZ coordinates. And then later on in the piece, we're going to cover UV coordinates and how points actually interact with other pieces of geometry, such as surfaces.
Cool. So I'll take over for a bit here. Basically, points are exactly like we may have learned way back in geometry school, right? You've got a coordinate grid and you want to sort of define a point in space. You give it an X value, you go along the coordinate grid, you give a Y value, you go up the coordinate grid, and that's where our point may be. These are, of course, 3D as well. We've got that Z axis that pops off that original graph paper, right? They can also be defined by parameter values on other objects. Point at parameter, 0.5 on a curve, or point at UV parameter, 0.25, 0.75 on a surface also is a thing. But in order to really understand that, we first have to get to those geometry types. So we are going to bounce around a little bit. Now, one thing I did want to highlight, a lot of people sort of realize, we can just give a number value to those XYZ values, but Dynamo also has an interactive piece that many just don't know about. So you can start as long as your graph's in automatic run mode, right? So we have to have that automatic mode sort of ticked off down there. If you can initially select whatever geometry node might create your point, you'll see when I sort of pick that, I got that little gimbal on that screen right there in my background preview right around the point, right? So it's got some arrows that sort of exist and say there's stuff moving on X, Y, Z axes here. What would you like to do? So with that node selected, I can then go into my background preview. I can do Control B or hold down Escape, or more likely just click here when we're first getting started. And then once I do that, bring my mouse down here. Notice we got that really long extension line that just sort of extended out following that red arrow. Once I do that, I can drag that arrow to wherever else I might want it on screen on the X, Y, or Z axis. And what you may not have noticed, if I go back one step before dragging it and then look at it here, we also had a slight change up here in that number slider being automatically added onto the graph. Switching back to the node view up there, you can see that's been added, and that value's been sort of set to wherever we might want it to sort of sit. So we can look at this a little bit more in live demo if this is something you guys would like to check out a little bit later. But for now, let's continue moving on with curves.
Cool. So Yeah, so one case in point with what Jacob just showed around the points is that this can be really interesting if you don't quite know the parameter range or the XYZ space that you're looking to work in. It can be really nice to be able to just place a singular point, move it manually to where your eye knows it to be correct. And then you can sort of post-rationalize that after the fact as well. So points are pretty simple. I think everybody has a pretty good grasp on what a point is. It's defined by 3 spaces, as Jacob just said. And then if we move on to a sort of more complex model type, we move into the curve space. So the curve has a series of different subsets. These are things like lines or polygons or arcs, ellipses, polycurves, and so on. And if we jump to the next slide, we'll see a representation of a bunch of different things. So you know, we don't have anyone unmuted right now, but basically, could you name these things if you saw them? Right now, we have number 1 as being the arc, number 2 as being the engon or the polygon, number 3 as being the curve, sorry, the line, which is derived from a curve, a circle, an ellipse. Moving on to number 5, a square, a NURBS curve, and then also a polycurve at the tail end as well. So all of these are representations of the curve class. So be it a line that is unbounded or be it a line that is bounded, everything here in Dynamo and in the Dynamo world is called a curve. And so you'll notice if you're playing in Dynamo and you're looking through the library, they're going to be under the categorization of curve itself. And so anything that can work on a curve can actually work on all of these things as well. So if you want to explode these or you want to get a point along that parameter space, as Jacob said, this is the kind of interactions you can do on any kind of curve object, which is what you see on screen right now. So these are typically defined by points or other curves. So on the instance, of polycurves, these are curves made up of multiple curves. In the instance of polygons, these are lines that are joined or derived from points that are joined together as well. So these are all instances of curves inside the Dynamo space. Everything is a curve. And if we move on to the next one, Jacob's going to talk a little bit deeper about a special case of curves called NURBS curves.
Yeah, NURBS curves are much more complex. All right, they are not uniform. It's literally in the name, non-uniform rational basis spline, NURBS, right? So because of that, things get really difficult in many cases. One thing to note before we really get into NURBS curves, we got to set some real ground rules in terms of what makes up a curve. First up, curves are always sort of only moving in one dimension, right? So they're kind of one-dimensional objects within that larger 3-dimensional space. Now, all curves do have sort of that start point and the end point. These can be the exact same point. That would be a closed curve, but they do have to have 2 separate values that are sort of listed to those pieces. They're also defined basically by this infinite number of points that just follow that one-dimensional path, right? It only goes one sort of way. And then curves are also can have no sort of gaps in that shape. So if we think back to, I don't know, classic AutoCAD, right? So we'll bring up some of Sean's heyday here, right? A dashed line, that's actually multiple curves, right? It's not a single element under the hood. It's multiple segments of curves in the end, sort of computationally speaking anyways. So no gaps. They also can't branch. So I can draw the letter L as a curve, but I can't draw the letter Y. I have to go back over myself, or I'd have to sort of split out in 2 directions. All of those things are no-goes. As long as you don't do that, you can have a curve. Now, curves, the NURBS curves, the way I like to think of them is it's shoelaces. They can be sort of pulled taut. I can grab 2 ends of the shoelace and pull it really tight, and I'm going to get a perfectly straight line where I'm sort of evenly pulling on both ends. If I pull a little bit harder on this end, but don't pull as hard on this end, it's going to sort of deform that curve a little bit. So on and so forth. I can tie shoelaces together and do all these other things. Every time I grab a point on the shoelace and pull it around, I'm deforming that curve. So one way to think of it, if you think just 3 points in space, like I have on the right side of the screen here, if you just sort of think through, what would a spline that goes through all of those curves sort of look like, right? Everybody's got something like that in their head. Maybe it's sort of a perfect arc, probably the one that sort of comes up off the top of your head, but it's highly unlikely that you perfectly matched any of the many curves that I'm drawing on here at this time, right? We've got tons of stuff showing up and they're all very different. And towards that end, it can make it really difficult to sort of manage to pull that content around. And that's because how you're pulling on any given point and where you're pulling to and how hard you're pulling all sort of matters in sort of the definition of that NURBS curve. So, all right, let's jump a little bit back in time here. Let's go back to point at parameter. So for our uniform curves, it's really straightforward when we start to talk about parameterization, right? You can sort of think of it as a percentage of the curve. And you can see that happening down at the lowest sort of graphic in this animation that we have here. We're starting at 0% of the curve, the very start point of the curve. We're going all the way up to 100, and it's moving sort of this consistent distance in between each individual piece. That middle curve, however, that's a non-uniform curve. We're pulling much harder on the right side on the end than we were pulling at the start. And as a result, the point's moving really, really quick, right? 0.5 is almost at the very end of the line, and then it starts to slow down in terms of the speed at which it goes in between there. And that starts to make probably a little bit more sense when you look at that top curve where we've sort of pulled that one piece up as opposed to just to the end. We've also displaced it on the y-axis to really get it there. The way you can think of curve parameterization with NURBS curves where it's non-uniform, think of it like driving your car into the grocery store, right? We're going to write down every time we turn the steering wheel in any bit, we're going to write down where that happened within the overall length of our path. Every time we accelerate, we're going to write down that. Every time we hit the brake to slow down, we're going to sort of do that same thing. And all of those sort of steps to draw that path that gets your car from your parking spot at home off to the grocery store, all of that stuff gets sort of written down in that sort of series of parameters over the length of the curve's path. Hopefully that made some good sense. Anything to add there, Sol?
Yeah, so you can also kind of conceptually think about NURBS curves and specifically as the points that derive those, or the control points, are kind of like gravity pieces, right? So if you've got more points at one place, there's a higher gravity towards that. So this is kind of referenced in the second curve on screen right now as far as Jacob goes. There's a higher gravity towards the right-hand side of that curve. So there's more control points over there, which is the strength of the NURBS curve is stronger over there. Therefore, the way that it plays through that is softer or slower and faster, further away from that gravity pull.
Gravity is a great analogy on that. All right, let's move on to surfaces. So surfaces are the next piece of sort of hierarchy in terms of complexity as we sort of move up our ladder of geometry types. There are a little bit less types within surfaces. We've got our NURBS surfaces and our poly surfaces. All surfaces in Dynamo are basically NURBS surfaces because poly surfaces are really just mini NURBS surfaces. Typically, I find these defined by either boundaries, right, where we want to sort of patch a closed loop. You might also loft in between two curves, which is sort of partial definition of boundaries. Or if you've got sort of a three-dimensional piece, often I find those have been defined through rather than boundaries, but by sort of that ordered series of points. You can get some really cool sort of topological features like you see there, and what I was originally envisioning as a sort of wall feature, but I don't know that that necessarily comes through looking at this after the fact. Now, each surface does have its own unique sort of coordinate system as well. So that allows us to sort of understand where things might fit. Now, similar to our curve parameterization, this is parameterization of the surface.
Right, so as you'll notice on screen right now, we have a little animation going on the right-hand side that starts to show where those parameterization values live. So with surface parameterization, we use these two notions of a thing called a U and a V, which is, you can conceptually think of basically as like the surfaces X and Y. It's just not using X and Y because that would confuse the space within the general world coordinate space. So U and V is typical across any platform, any program, any application, or inside of Autodesk and outside. And this parameterization, again, uses the same analogy that Jacob used before as percentiles. So at the upper bounds, you're going to have 0, and at the lower bounds, you're going to have 100%. In any space within that matrix, in both the U and the V way, we'll have a percentile of U and a percentile of V on it. So you'll notice as this surface here is jumping around or bouncing through or waving down from upper left to lower right, you'll see that those UV locations are actually moving in space as well. And what that means is as you deform the surface, as you make changes to that surface, then those UV parameters are going to take into account those changes and make sure that they're still proportionally or representationally accurate to that percentile after that deformation. So the same surface going through a deformation is going to have the UVs in slightly different locations, but overall to that surface itself, they're going to be consistently accurate. Cool, so this is another representation of showing how UV works. This is taking a point and running through Jacob's funky wall geometry here on the right-hand side. So any point on the surface can be defined by using a notion of surface.parameter at point. So as we touched upon earlier, we had the point section, which was just a singular slide, and we said, look, we're going to talk about UV coordinates later. And so this is really where this comes into account now that we have a conception of what a surface is. So that you can find or derive a point on any surface, irrespective of how complex it is, as you can see on your screen right now, based on those UV coordinates. And remember that they are proportionally accurate, they're percentile in nature. And so this ball here is basically running around the surface. And if you took the surface from a bird's eye view and looked at it moving, you would notice that there'll be this gravity weighting to it. It'll be moving faster or slower based on the Z coordinates. But overall, if you took a map and ran sort of an XY on that flat surface, you'd see this point basically corresponds, not perfectly, but basically corresponds to the XY corresponding to the UV in this instance.
Yeah. Now, one thing to mention about parameters is they don't have to fall on the object itself either, right? So within the bounds of a curve, you could say point at parameter 2, which would be on a perfect line, twice the length of that line, or point at parameter -1, which would be one length of the line before that line. And that extends out to surfaces as well.
Cool.
Let's
so
move on.
The next,
oh,
sorry,
go ahead.
I was going to say the next thing we're going to start covering is the solid typology. So this is cuboids, spheres, cones, and cylinders. So if you imagine a surface as being like infinitesimally flat, solid is made up of those and contains that bounded volume inside as being solid stuff. So the same kind of approach we had with the images for these surfaces, we can have watertight geometries here associated with primitive types called solids. So where you have thickened the edges of the surfaces of all of these geometry types. And this allows for really interesting things. So you can extrude some really funky shapes, but you can also do really interesting operations with Boolean operations. So this is the adding to or subtracting from pieces of geometry from other pieces of geometry. These are reasonably slow just across the board as an operation in math, but they are actually very, very accurate. And Dynamo does handle solid operations very, very well. You can do some really interesting things with solids as well, which we'll probably touch upon at a later date, but you can actually have non-joined geometries becoming the same piece of geometry and having operations ran across those as well. So there's some very funky sort of deep operations you can do with solids.
Cool. All right, and then last but not least in our geometry hierarchy are meshes. Meshes are far and away the most complex in terms of sort of how they're described, right? There's no sort of simple mathematical way to define a mesh because we have to sort of define each and every one of those points and then talk about the relationship between each point that defines each edge, and then each three edges defines that surface. It gets really, really complex. One of the ways I like to sort of conceptually think about them is sort of like they're topologies with a representation. The mesh itself is sort of all the faces. We can pull out any individual face from the mesh, any individual sort of set of vertices that define the mesh. But overall speaking, these things are slow. If you do need to work with them, and you will find you often have to if you're doing stuff like topography, I recommend going to the Mesh Toolkit package. It's extremely, extremely powerful relative to the out-of-the-box nodes that Dynamo sort of comes with. So go ahead and download that package. That is one of the Autodesk authored packages, and tons of great stuff in there in terms of what you can do with it.
Yeah, and to add on to that as well, we're currently actually upgrading the Mesh Toolkit package. So there's going to be some interesting updates in the not too distant future as well. So we're also looking to expose that out of the box. So a little like a FYI or a sneak peek to the future state of the Mesh Toolkit package.
I am super excited for that. Good, awesome news to hear. Thanks, all. All right.
Cool. So this is what we may or may not have some technical difficulties with. So I made a GIF of this. And so this was alluded to in the last talk we did on abstract geometry. So we're talking about how we can potentially string all these things together and generate some really cool things. So in this instance, this is an operation of a slatted facade I made actually a few years ago. This is an evolution of that. So this is a new graph I've built over the last week or so that starts taking some geometry from Revit in this case. So the singular surface you see with the two window holes and the door at the end comes from the Revit sample file. Everybody is probably pretty familiar with this, the house that comes shipped with Revit. And so what I wanted to do was just generate some funky architectural facade that runs on top of this, but also take into account the windows and the doors as well. So what this GIF is showing you is an approach, and bear in mind that there are many different ways to approach working with geometry inside of Dynamo, and they all have different trade-offs in terms of speed or performance versus ease of use or ease of understandability. And so what I'm doing is I'm taking that surface and I'm using this notion of ISO lines to basically dissect that surface across the parameter space. So as we talked about today, I'm taking from 0 to 1 as the parameter space, so from 0% to 100%, and then equidistantly spacing lines across that. And once I have those lines, I'm then intersecting those lines with the geometry or the base geometry, because when you build ISO curves, it doesn't take into account the holes. It just takes into account the overall nature or the overall bounding box of that surface. And so once I intersect that with the surface, you'll see then we take out that door and we take out those windows. And from that line, I'm then extruding that line out to the thickness that I want my slats to be. I'm then thickening those slats to make them representational, as opposed to being infinitesimally short. And you can conceptually think of this as being made out of timber. And once I have those, then what I'm doing is I'm surfacing the outside curves of these, taking those curves, extruding them upwards and downwards to generate then points on that, to then generate what I call these cutting tools or these cutting objects. And so these are a series of randomly generated circles on planes that have been built from those points, and then they're extruded along each other. So this is a notion that you could generate multiple different variants of. So you could use this graph to go and say, I want to generate a slatted facade, but I want to generate, say, like 20 of them and just pick the one that I like the best. And so once we've done that, then it looks like the GIF has stopped, but that's cool. Once we've done that, we have the windows, which I also take. So I can take the interior surface geometry of that plane and understand what is a window in that instance, offset and extrude out in the same way. So we can have a window boxing put into this. So this is what we're going to attempt to live demo. This is a little bit of a teaser. I'm talking through it in depth right now because we had mild technical difficulties. I had to actually update my parallels. So Jacob's going to drive and we can talk through and show how the graph is actually set up a little bit better.
Give me 1 second to open the file here on my other monitor.
So while Jacob's doing that, this is an instance of the kind of thing you can do. And once you have that geometry inside of Dynamo, you can then push that to other places. So Dynamo allows you to export to SAT files or export to STL files. You can also use other nodes that come from packages or out of the box in things such as the Revit, Dynamo Revit workflows to then push that back into your host of choice. So you could push this back as individual families. You could then start attributing data back to those. You could start using sort of downstream Revit workflows in that, utilizing cool things to do geometry for, say, shadow, do visualizations, or start to understand how to pull this and manufacture this by pulling the actual curve geometry of these and putting that into a 2D plane for a CNC routing operation or the like. So what you see on your screen right now is the end result. So I have colorized it with a sort of a gray fade, like a gray blue to a blue fade. And this is the kind of thing that would then get pushed back into Revit. If you look at the graph itself, it's made up of sort of 3 or 4 major sections in green or CN right now. And this is generating the base slats. So the first one generates the base slats, the second one creates those cutting tools, the third one generates the windows or collects the exterior curves to generate those windows, the next one creates the windows, and then the last white one is a visualization just to change the color. So the intention with a working parallels, also windows for myself, was to then step through this using the orange sort of like visualization application here. So if we can try this and see if this works, Jacob, we'll see how we go. It should only take like a few seconds to run because Dynamo uses a pretty smart application of a thing called delta compute, which means that if a geometry node hasn't received any changes, then it's actually not going to recompute that. It's just going to spit out the same result. So depending on the setup of your graph, you could either have a graph that has to re-execute every single node every time, or you should be able to have a graph that doesn't. For some reason, I didn't set this up appropriately, so my apologies. This should just be re-executing the final node that you see in the orange space right now as opposed to the other, but I do have randomization nodes that are shuffling things. So that is causing a forced re-execution of things downstream from there. But without further ado, knowing that we're now running and Zoom causes funky issues trying to run things over it, we can probably run to the Q&A, and I am happy to give this graph out to anyone who has participated or anyone else who finds it after the fact as well. So we should be able to post this into the thread from this presentation as well. And it is reasonably heavily annotated to explain what is going on in every instance. From a conceptual level, just to explain how things are working. It uses a little bit of design script, but not too much. It's mostly a node-based workflow. And one interesting thing here is the data.remember node at the front. So I'm actually pulling Revit geometry. So you can use this graph either in Sandbox or in Dynamo for Revit, or any Dynamo for any other flavor for that point. Cool. You do get the option to change some of the inputs. So choose the amount of cutting tools and the thickness of things and the amount of slats and so on. I'm
going to spin up a second instance of Dynamo in the background, and we can try and freeze everything and then look at individual pieces one by one if that's what people would like to see. But in the meantime, any questions, feel free to raise your hand and we can take people off mute, or we can answer questions that you might have directly in the chat.
And so one case in point is when I was running this yesterday before I updated my parallels, it was taking about 2 seconds to re-execute every time. And right now it's doing other things. So I can investigate and try and fix that before I post it.
Yeah, it is running everything all the way through each time by the looks of it, just because of that remember node.
Cool. So please do sing out with any questions you might have about anything you've seen today or anything else Dynamo related whatsoever. More than happy to help, more than happy to answer any of your questions and get deeper into any of the topics that we've covered, or deeper into any other topic that might tickle your fancy.
Cool. While we wait for any questions, I will do another quick demo, sort of actually showing how that sort of point manipulation that I showed before works. So what I'm going to do, I'm going to sort of right click to sort of hot search. To do this, right click and then just start typing right away. I'm going to place a point. Notice if I right click and then I click a second time, even if I click right in that search period, that search window goes away. It automatically places your cursor. Now I am in automatic run mode, so you can see when I click on this node, that gimbal is going to show up around the node itself. And now when I go over into background preview, I can start to manipulate this, and my number slider has shown up directly right away. Now this does work on multiple pieces, so we're not sort of limited to just sort of X, Y either. If I had a point by coordinates, I'm going to make some math.random list. We'll make, I don't know, 10 points randomly on the Y axis. These numbers are going to be defined between 1 and 0, or 0 and 1. So I'm going to multiply this by 10. So now they're going to be between 0 and 10. We'll feed that in as my Y value, and then I'm going to feed in a series from 0 to 9 as my X value. And so you can see I've built a series of random points. And I'm going to say NURBS curve by points. Got to type all the way. There we go. So I'll put my NURBS curve by points node on there, and you can see we get this sort of random shape. And if I don't like my random shape, I can just generate a new random list and we'll get a new random shape. But from here, I'm going to hide all of these points. And then point curve dot point at parameter. So without defining the parameter, notice I now get that blue arrow as opposed to the multiple arrows. So we're going to pop back over here. I can now drag this, and it's going to allow me to pick a point randomly, not necessarily, but manually, so I can get a little bit more sort of expressional with this sort of placement than what I could get maybe with sort of placing in a number slider and locating it that way. But you can sort of see how that works out. And if I got sort of really aggressive with that, I can actually pull this out beyond the end of the line. No, notice we are constrained to the length of the object in this particular instance. However, if I come back here and I say, let's get the parameter value at 1.5, my point is all the way up here because we're not limited to the length of the curve by typing that content directly. All right, there are some questions in chat now. Francis, did you want to speak up on that, or do you want us to just discuss this a little bit more in?
So Francis, I have written an answer, but I'm more than happy to talk to this. Please do let me know if it doesn't make sense to you.
Can you hear me?
Yes.
Yes.
All right. Well, first of all, English is my second language, so it might be difficult, but I'll try. So I was trying to get a solid or a geometry from my walls, and get the bottom surface, so that way I can get the perimeter curve, and it will allow me to get the wall thickness, because otherwise I was struggling to get the thickness of the walls. And my first goal was to create some formwork panels. So I was trying to create some new plans to do so, but I never succeed to extract the bottom surface only. So I don't have any reference to place my new walls on my concrete walls, and I was trying to figure out how to do so. And I don't know if it's more clearer, if you understand better the goal of the task.
I absolutely do, and there's a few different ways you can tackle this. So it's one of those really common questions that we see from people. I specifically deal with it. Oftentimes it's after the fact sort of generative questions, or we want to sort of define information about rooms, so we need to find sort of a consistent working plane. There's a few different ways you can do that. If you just need a plane, you could always intersect a plane with the solid geometry, and that's going to do it pretty quick. But in many cases, you just want all the surfaces that point down or all the surfaces that point up, because the ones that are up, those are going to be our roofs. The ones that are pointing down, that's going to be our floor. The ones that point any kind of other direction are walls, if we're doing basic geometry. I'm going to go ahead and delete these nodes for now, but I've defined a random cuboid here, and maybe not too random, it's just 10 by 10, right? And then we can do an explode node. And this is going to break that cuboid down into its core parts. So you can see I now have 6 different surfaces. Each one of those surfaces faces a different direction. So when I click through my list, you can see it here. Oh, there it is. We're looking for the one that's at index 1, but manually going through and clicking that doesn't necessarily make sense, right? There is this great node in Clockwork. It's been there for a while. There are similar nodes in, I believe Crumple has one, Gavin Crump's package, and a few other packages as well. But you can put this in, and it's going to basically say, let's look at stuff that's just horizontal down. I'm going to take all of this and say, hide all that geometry preview. And now I'm able to look at just the pieces of my wall that point down. Now this can be 80% of the way there. And the reason I say that, you can imagine if I had a window running through my wall, it's also going to get the underside of the head of the window, right? So the next piece that you'd probably want to do is filter based on the Z height, which Sol sort of spoke to there. But one of the reasons I do love Clockwork is it basically does gives you the opportunity to sort of pull it apart and see how it works. Because it is a custom node, we can double click on that, and sure enough, what Sol described is basically what's happening here, right? It's taking our surface as our input. It's finding the normal at parameter 0.5, so the midpoint of the surface, and it's finding out what is sort of the tangent vector to that piece, pulling that Z value. If it's saying it's almost equal to 0, then it's going to be vertical, otherwise not. And then it can give us our is vertical filter here, is horizontal up, is horizontal down, all of this stuff by just basing that data off those initial sort of vectors. So you do have to have kind of a good understanding of not just the content we covered today, but also the previous content, because again, that's where we talked about vectors. But yeah, it's doable pretty quickly right there.
Yeah, so to add on to that, Francis, there's different approaches, right? And they'll come with trade-offs. So Andreas's approach uses vectors, which is awesome, right? It's using abstract geometry. So as we discussed last time, it's faster than using real geometry. The approach I wrote out in chat is so that you can visualize what is going on. So the conception here is exactly the same as Jacob showed. You have your geometry, in this case a cuboid, you explode it, you get a series of different surfaces. You, instead of doing the vector approach, you can also do this with the placement of points. And so if you have those points, then you can just query the Z value of what those points are and basically do a filter operation using the index of that Z value. based on the index of that surface to do exactly the same, or to find exactly the same result. So there's many different ways to do this, and it depends where you're trying to get this geometry from as well. If you're trying to get this geometry from Revit, you might also be able to pull the location line and get the location line intersection with the surfaces that are exploded, or you can potentially pull that information in a numerical or a data perspective by just querying the actual Revit API. There's nodes out there that would potentially do this to give you the thickness of the wall as well. So it kind of depends like what the kind of approach you want to have that works for you. And sometimes there's trade-offs associated with understandability or legibility compared to sort of some heavy math. And so like for myself, I do both. I like the performance gains that math gives you, the abstract geometry uses where I can, but sometimes it's actually more important for me to actually understand what's going on or to showcase to other people what is going on. And therefore using physical or model geometry types, which I've talked about today, is another way to showcase how that works. Because then you can use color operations to say, all right, I want to color everything based on different Z values. So, you know, it's going to be red at 0 and it's going to be, you know, green at 100, and that's going to show you the variance of where those things correlate to. So depending on how you want to achieve your solution, there is many different ways to get there.
You guys are genius. I love you so much. I was trying to figure out how to do it, and I was like, it never works. And I was trying to get like the height of the walls and everything. But now with the two surface, horizontal up and down, I'm gonna be able to get the top and the bottom. So my new wall is gonna be exactly the correct size for the panels, and then I can just make a new node with adding 6 inches on the top for the concrete, and it's gonna fit perfectly. So I'll be able to get all the walls and do almost all the walls at the same time instead of doing it manually. It's gonna be, my boss gonna like me a lot. Thanks for my future raise.
Yeah, you're most welcome. And one thing that you'll notice as well is like what we've done in this operation is we're taking a thing, we're exploding it into its component pieces, then we're using sort of operations to manipulate those pieces to figure out what is going on before we reconstitute that or make that back into a different thing. So there's a lot of workflows that Dynamo uses like this. It takes something, Jacob's kind of showing this right now with the minimum item by key. You're taking a stream or a sort of a branch of that stuff to find downstream operations to use to then go back up to the higher level and work with that original geometry. So there's many different, like I said, there's many different approaches, and Dynamo allows you to get very, very granular and start to break things down into their component pieces to work with them. So you'll notice that all of these custom nodes that do really, really cool things, like the clockwork node that Jacob shows, uses either a series of just out of the box nodes to achieve what they're trying to do by breaking things down, or sometimes they leverage some sort of higher level things using, say, Python and talking directly to APIs and doing funky things too.
Thank you very much, guys. You're awesome.
Glad we could help out.
Yeah, likewise.
Yeah. All right. Any other questions from anybody else?
Now, speak now or forever hold your point.
Right on topic with the pun there. That was great.
I'm starting to learn this stuff.
All right, so Sean, you're presenting the next one, right?
I believe so. If Jacob will cue that up.
No, I meant the next Dynamo.
No. I'm getting smarter by being around you and Jacob. I am not anywhere to that level. So I'm still trying to get the concept that even a line is a curve.
Yeah, it's a little difficult. How do we put this? So technical terms are expressed inside of Dynamo. And so technically a line is a curve, and technically a circle is a curve, and technically many other things. But once you start to wrap your head around how these things piece together, and you can see this in the library as well. So if you look over in the library like Jacob has right now, if he just goes to curves, everything under curves is considered a curve. So arcs, curves, ellipses, ellipse arcs, helixes, a whole bunch of different things, which means the cool thing about this is that anything that works on a curve is going to work on all of those things as well. So you don't need to have, say, circle.explode or a line.explode or a surface.explode or a solid.explode, you'd have like 500 different operations that you can achieve in one singular one, which is just geometry.explode, because curve is also underneath the moniker of geometry. So anything that works at the geometrical level is going to work on curves, and anything that is a curve is going to have any curve operation that works on it. So while it is conceptually a little bit difficult to wrap your head around at the outset, it starts to make sense and starts to show you how incredibly powerful it actually is to have this set up this way.
Yeah, it's like trying to grasp the concept of the universe is never ending.
Yeah,
yes.
exactly.
Yeah, but I mean, that's really sort of the key aspect for me. You know, I talk to a lot of people who are frustrated by this sort of early on, and how do I understand like what I can use? And it really comes back to that sort of idea. And we talked about it the other day, I think in the first session way back when. So it's probably worth sort of reiterating. Like if I'm looking through my library for something, I'm going to go to the geometry section of the library because I want to talk about geometry, and then I'm going to go to the curves bookcase. Then I can go to any bookshelf on there and pull out a whole bunch of stuff, but everything is still under a curve. So anything that works here is going to work other spots too, right? So we can create content, that's the green plus mark, modify content, the red lightning bolt, and query information about content, the blue question mark. So, all right, any other questions? Chat's a little quiet today.
Come on, Carl, I know you have a question.
Carl always
Put you on the spot. Maybe actually Carl's a master of this stuff. He doesn't need to ask questions.
All right. Well, yeah, I guess if not, I guess we should probably plan on having sort of backup presentations ready to go for the next time out. But I'll go ahead and we can look at sort of breaking down Sol's graphs a little bit more complexly here. So I'm going to come back to here. I'm going to go ahead and just freeze a whole bunch of sections so that we can talk about what each one of these do. I'm also going to turn off the preview on this guy.
And Simon has a question.
Oh, we do have a question.
Yes.
Can you import third-party geometry like SketchUp using Dynamo to translate into Revit? There is a package out there that gets at that. I can't remember what it is. Do you offhand, Sol?
I don't remember the SketchUp specific package. So the short answer, Simon, is yes. So the way Dynamo is built is that you can kind of do almost anything with it if somebody has built that for you. So the package manager, which Jacob is showing right now, is community content that people have uploaded. And there's a bunch of really, really, really cool stuff there. So if you're curious about these kind of questions, just have a quick keyword search this. You might find something like we have on screen right now. I personally haven't used this SketchUp for Dynamo, but you can import generic types into Dynamo as it stands right now. So SAT files, some DWG types, and a bunch of different things. In the future, we're actually looking to expose more things that you can import into Dynamo out of the box as well. So that's another little sneak peek. But please do check out the package manager and have a quick look at the sort of packages on offer. And you should, in most instances, be able to find something that does what you're looking for. At the very least, in the worst case, you should be able to export your SketchUp file into some sort of more common data format, such as SAT file or STL file, and import that into Dynamo as well.
Well said. Yeah, it really gets at the point that a lot of our BIM data, like we think of, you know, BIM, building information model. It's not that you're building a 3D model. That's not what information model stands for. It's that we have an information model, just like you might have with, you know, your MP3 library back in the day. And it's all about relationships between pieces of information, and geometry is information in the end.
Exactly. And Donia, yes, we will be posting this stuff to the community conversations. And once I fix the graph, I'll post this as well, so you guys can have a play with it.
Yeah, I'm going to go ahead and I'm just going to do a series of sort of freezes here, and then we can just look at each one in particular, or other people who might have questions, put them in the chat. Feel free to bring them up as you may think of them, and we'll keep an eye on that as well. So you can see the first thing that we did here is we got that sort of source geometry in Sol's graph. And then right off the bat, he uses this curve by isocurve on surface. So when I turn, whoops, I did the wrong thing there. I meant to turn the preview on. So you can sort of see what that does is he's just basically making all those little lines across the entire surface of the piece. From there, he's going to intersect that with the geometry of the surface itself. So it sort of trims it up to the extent of the surface, right? Flattens that out to make sure we get the other content, and then we start to sort of give it a real form, right? So turning this piece on, you can see it turns it into those blades, gives the blades an actual thickness at this piece. So now this is starting to look more like, I don't know, a 2x12 on the face of the building, perhaps. So I don't know what your dimensions were.
Yeah, I don't come from America, so I don't use imperial. So there might be another point for this graph. Please don't hate me if you open it and it goes bonkers if you're using you know, the imperial system. I did use metric for this.
Yeah. All right, so whatever you refer to a 2x12 in metric format as, and then that gets us sort of that first piece, right? And then I'm going to stop here because you can see this jumps way out over here to do the sort of formal modeling. But before we finish that, he's taken the first and last curve here. I'm going to unfreeze that. I'm going to go ahead and preview this off, preview this off, and preview this off, so we can start to see these pieces.
Funky tip, Jacob, you can select multiple things and hide them at once with your turn geometry preview off.
That's right. I'll make sure to show that in the sort of the next piece here. So I'm going to turn the preview on this piece, and you can see he's grabbed just those inlines. It did that with a little bit of sort of list indexing, right? So curves, my full set of curves as a list, the first sublist of curves, the first item in the first sublist, and then curves index 0 gets us that first sublist of curves, and then the last item in the list, and he does that by list.count, and then takes the list of curves in the sublist and gets the very last one and subtracts 1 from that number. I think you could actually use just the -1 in the brackets here, which might make things a little bit more fun, but list indexing is probably a session for another day, right? Then we're going to take that
slightly more advanced topic.
Oh yeah. Then we're going to take that and we're going to he translates that geometry, and that's another sort of fancy word for move. We're going to talk about sort of manipulating geometry in the next session. So you can see that moves the curve from where it was here, and it's moving both of them, right? Because we're working with this as a list of multiple objects, puts them out there, extends the start on them and extends the end on both of those curves so that they get a little bit longer. We'll look at this with both of those on. So longer curves right there now.
Yeah, and the reason for that is, so extending the start and extending the end. Once I've extended the start, that curve has an extended start. So extending the end of that is extending the already extended curve. It's a little bit funky conceptually. But the reason I'm doing this as well is if I didn't extend those curves and I had those cutting tools that are coming down through, it's going to make the actual resulting geometry look a lot worse. So there's a chance that you might even want to extend the curves a little bit more depending on the aesthetic output you want to have. But it means that the slicing planes, as things are crossing over each other, is now going to be more spread over the course of that surface as opposed to being tighter and then having triangles at the center point of the bottom and the top curves not being dissected.
Yep. And you can see he's distributed some points using point at parameter, which we talked about earlier today. Takes those points, builds some vectors, and translates them around in what looks to be a sort of somewhat randomized perspective here, but the new list of points, when I preview that, it's going to basically, it's just shifting them inboard a little.
So it should be shifting them out. I think the perspective's a bit, okay, maybe this is where I made a mistake. But in essence, I should be shifting those out so that the slicing plane actually slices every single slat.
Got it.
Yeah. Oops. I'll fix that.
So builds those vectors, builds a plane of them, and then uses that plane from each one of these points. And again, from that last session, and we will post the links up. And Kate actually did us a great favor because I did see the question in the chat about the other previous recordings. You can watch those on that YouTube channel right there. which will be really good. But so now with those sort of points, planes defined, shuffles the list so that the planes are not in a consistent order, and then creates a circle on each plane, and then lofts each one of those circles into a solid. And that's where we get sort of this continuous sort of fun little grouping. Now he does also have sort of a randomization there in terms of what the radius is. And again, that gets a little bit design scripty, so that's probably a bit more advanced than we have time to cover. I am cognizant of the time. And then finally here, we'll turn this preview on. This is the intersection of all of those slats with all of that other geometry. And I will do these, select everything, right click on my workspace background and say hide all geometry preview. And now we have our slats sort of created in this particular node. Before finally, last but not least, down here, I've got to unfreeze the right node, defining the color range, unfreeze the right node.
You have to go back upstream for that.
I have to go
There's
all
also
the
the
way
window
back there because
workflow.
I forgot this. Yeah, I forgot about the window workflow. We're going to skip over that just in the interest of time, but now you can see this content's been done. And then when I turn on the preview on this, we should start to see, I think.
So one thing on screen right now, you'll notice if you have multiple pieces of geometry on top of each other and they're exactly the same size. So in this case, I had the gray geometry and then I had the blue coloration. They're going to fight each other in the Z value and the XY value. So you have to turn off other geometrical pieces you don't want to see if you want to have sort of a visualization component at the tail end.
Yeah. So, but yeah, that's the whole graph all the way through, which is a pretty cool workflow. We can break down sort of similar stuff like this in the next one.
Yeah, and I know we've only got sort of 5 minutes left, but we do have a couple of questions in the chat. So one of the questions was coming from Francis again. How do you usually group elements? Sorry, I usually group elements by parameter, otherwise I use string to group by key, but it never works. So Francis, would you be able to explain why string dot, do you use string dot from object to create strings? We might need to unmute.
Oh yeah, sorry. Yeah, well, I said string. Well, it can be any. I don't know. For example, yeah, if I use objects, for example, I don't succeed at all to group them by any specific thing. For example, a group that is by z point. Well, I can extract the z point, but then I cannot, for example, group them by the same value. If for example, I'm using the key value or number or anything like that, it never groups them. So I don't know,
Right.
other than get the perimeter, get value by, well, get value at perimeter, it never works in any way. And I was trying to figure out why.
Yeah, so there's a chance that the numbers that you're pulling are minutely different to the other numbers that you're trying to group them with. So if you wouldn't mind just posting your question in the community conversations, we can loop back to that one because I think it might take longer than a couple of minutes to explain.
Awesome, thank you.
Cool, you're welcome. And then Jan Willem, I just started trying the next tips. How do you divide a solid or shape with a void into rectangles? So would you be able to unmute and very briefly explain what you're asking here, Jan?
What was the name? I'm so sorry.
Jan.
Okay,
Jan.
got him. Thanks.
Yes. Okay. I try to. It's almost a wall with windows in it, with one solid, and we put voids in it to make the window. And now someone is asking, we want that in rectangles.
Oh, to like sort of split the solid up into smaller pieces.
Yes. Or in new solids. That's
right.
But
okay, so one of the options.
Oh, sorry.
No, go ahead. Sorry.
Our workflow is we make it with parameters, so the voids are all in parameters. That's the workflow. And now there's another question.
All right, so you can dissect geometry in many ways, and Jacob touched upon this briefly. So you can generate abstract geometry, in this case planes, and you can do that planes at parameter points to intersect and then slice that geometry up using solid.difference or geometry.intersect workflows. I guess we're coming up to time as well. Would you be able to also post your question into the community conversations as well, so we can have a look at that and give you a little bit more? Oh, you have? Okay, cool. So I haven't had a chance to look yet then, sorry. But we can loop back with you through that.
Yeah.
Would be nice.
Same thing with the point cloud question in there. The new Revit 2022 API does expose the recap API to some extent. So in theory, it's entirely doable, but it's going to require some degree of heavy lifting. Sean, let's go ahead and close it out because I know we've got like 60 seconds to wrap this up.
I hope it's not a race on 60 seconds, but thanks for everybody who attended, and Jacob and Sol and Kate. This has been a great session. If you're looking for other ways to connect and engage in the Autodesk community, we have other ways, and I hope, back to that last slide, I hope we see you on May 6th. But we have a few resources for you. You can explore the different Autodesk communities, including the global network user groups in the Autodesk group network, and our Autodesk industry-focused communities, helping colleagues solve business challenges together, the Autodesk forums, and staying connected with us on Twitter. You'll get those in the chat here in a minute. So thanks again, and we hope to see you on May 6th. It looks like we're going to be doing, let's see, what is it? Geometry modifications. So thank you.
I was asking too early.
Yeah, but we might be able to cover it more in depth next time as well. Yeah. Yeah. So modifications.
Thank you very much.
No problem.
Thanks everyone for attending. Absolute pleasure to hang out with you guys today.